All right, let's get going. It's a big honor for me to have an opportunity to speak at Gopal Prasad's birthday, 75th birthday celebration. I started working on applications of Prasad's volume formula about 20 years ago. I will talk more about how I came to this and more details later on during the talk. Soon after starting get familiar with the formula, I sent an email to Gopal Prasad with some very naive, as I understand now, questions, but Gopal answered immediately. And since then, whenever I ask him something, or as far as I know, other people ask him questions, young people ask questions, others ask questions, Gopal always comes with an answer. Later on, I had an opportunity to meet in person with Gopal and Indu, and then we've seen each other several times. And unfortunately, it was not possible to meet this year in Bangalore, but I'm looking forward. We are all looking forward for the future opportunity. And now I would like to start my talk. I dedicate my talk to Gopal and Indu Prasad. So, Prasad's volume formula and its applications. I'm going to talk mostly about my own personal encounters with Gopal Prasad's formula and some applications of this formula which I got involved. I will mention some other work. However, it's absolutely impossible to cover all phases of formula and its various applications in 1 hour. Well, I'm going to start with how I got to know the formula. And in order to do so, I will just give a very quick introduction to hyperbolic volumes of hyperbolic manifolds, because this was my first interest in volumes, and with that I got to know Prasad's volume formula. We consider hyperbolic n-dimensional space, for example, Lobachevsky Bolai-Apachov plane with this hyperbolic metric of constant negative curvature, -1. And well, there is also n-dimensional hyperbolic space. And let's consider its group of isometries, bijections which preserve the metric. You know this group by isom Hn. This is a Lie group, and it has some discrete subgroups. If you consider the quotient of the hyperbolic space by an action of the discrete subgroup, you get what is called hyperbolic orbifold. Whenever the group has no elements of finite order except the identity, the quotient will be will carry the smooth hyperbolic metric, so it will be hyperbolic manifold. The most interesting, at least the most interesting for us, will be the class of hyperbolic quotient spaces which have finite volume. Okay, in Euclidean analog, you can think about the group, say Euclidean plane, R2, the group of isometries of the plane, and there is a lattice there, that's Z square. When you mod up by this lattice, you get a torus. So this is a finite volume Euclidean two-dimensional manifold. Okay, we continue to say something about volumes of hyperbolic manifolds, and well, eventually orbifolds. So when dimension is even, 2, 4, 6, etc., Euler characteristic which can be computed from, say, combinatorics of a triangulation of the manifold, is non-zero, and generalized Gauss-Bonnet theorem tells that the volume is proportional to the hyperbolic volume is proportional to the Euler characteristic. For odd dimensions, the Euler characteristic is 0, but the volume is still, well, a non-trivial topological invariant, which is well, just one of the consequences of the celebrated most of Prasad rigidity theorem. This is the first time in my talk when we encounter Gopal Prasad's name. I'm not going to talk about rigidity theorem. Most of proof rigidity theorem in dimension 3, and Prasad proved it soon after Prasad proved it. Well, later on Prasad proved it in general, and so now it's well known, most of Prasad rigidity theorem. Now, if M is oriented connected hyperbolic manifold in any dimension, then there is also a Gromov-Thurston theorem which says that its hyperbolic volume is proportional to the simplicial volume, or what is it's also called Gromov norm. Well, volume is a measure of Gromov norm is, well, topological invariant of the manifold, which is it's a measure of complexity of the manifold. So this way, hyperbolic volume is also the measure of complexity. And here comes a natural question to find the simplest hyperbolic manifold or orbifold in a given dimension. In dimension 2, this simplest example is a so the simplest from the volume point of view orbifold will be Hurwitz, so-called 237 triangle group, and it has a large set of remarkable properties: geometrical, algebraic, and arithmetic properties. So, well, it's a well-known problem. I also knew about it. And when I came to, after my PhD in 2002, I came to Max Planck Institute in Bonn, and now by coincidence, but at that time I came for a postdoc, and I encountered this paper by Brent Everett and Colin McLachlan called Constructing Hyperbolic Manifolds. I will show a bit more of the abstract of this paper, in fact, the beginning of the abstract of this paper. You can see on the screen. It tells you how to, well, how Michael Davis constructed his 4-dimensional hyperbolic manifold of small volume, Euler characteristic 26, and it's very remarkable Davis manifold. So he took some Cox simplex and 4-dimensional simplex with particular angles in hyperbolic 4 space, and he proved that it has a finite sheeted cover, quite large degree, which is a smooth hyperbolic manifold. What Colin McLachlan and Brent Everett did in their paper, they explained how to obtain the same example using arithmetic groups. And at some point in the paper, so they have a quadratic form defined over field Q root 5, and then they consider reduction of this form, which is this quadratic form. What I forget what which prime. Okay, so you reduce this form, and the manifold, Davis manifold, come out naturally as a congruent subgroup of certain orthogonal units group. Well, when I looked at it, I thought, okay, why instead of the quadratic form which comes from the simplex, I take another quadratic form defined over field, say Q cosine 2 pi over 7, which is the field of definition of the Hurwitz group. And perhaps I do the same congruence construction, do I repeat everything? It's more or less clear how to do it if you know a little bit about arithmetic of quadratic forms. So you obtain, and some say Minkowski's lemma, you obtain smooth manifold. And okay, perhaps by an analogy with two-dimensional case, the volume of this smooth manifold will be smaller than the volume of considered by Mike Davis and then Avery McLaughlin. So this was my idea, and I could repeat all the steps of this paper, except that I didn't know how to calculate the volume, either of the base orbifold or of the quotient manifold. You can compute the index, but you still need to know one more number to calculate the volumes. So I started to look around, and I encountered that there is this paper by Gopal Prasad, which is called Volumes of S-Arithmetic Quotients of Semi-Simple Groups, published quite some time before, yeah, more than 10 years earlier. Well, and you start to read this paper. It's dedicated to Harishchandra, and the paper has appendix by Moshe Jordan and Gopal Prasad. And well, the purpose is twofold, and the first part is what was the most interesting to me, that claims in the introduction that we have a computable formula for the volumes of very general arithmetic quotients of whatever semi-simple algebraic group, but then through arithmetic groups you come to a construction to quotients of Lie groups, semi-simple Lie groups. Well, very good. So you continue reading the paper, and then you encounter the formula. It's closer to the end. The main theorem, 3.7, gives you the measure of the quotient space in terms of this expression, which has, as you can see, well, here are the quantities which appear in the formula. That's all very clearly stated in the paper. So there are some invariants of the Lie group, like dimension, rank, and Lie exponents. And so, well, arithmetic groups, they come together with a field of definitions. So the invariants of this field, like firstly discriminant, and so the discriminant of some extension, we can call it splitting field, comes into play. And then there are some numbers, and then there is Tamagawa number, and then there is something what is called Euler product. Well, so I found the formula, and I found it quite overwhelming, because, well, I must confess that when first I encountered the formula, I didn't know what an algebraic group is. So I knew that I could figure out that orthogonal groups are algebraic groups. So, and I was interested in orthogonal groups. So algebraic groups were relevant. However, the formula is complicated. You look at it, and you look at it for more time, and you look at it for more time, and you find, well, it's a very beautiful formula, but you find also that it's a practical formula. So, well, first, there are some terms. say, discriminants, some Lie exponents, which are possible to estimate, or sometimes when we fix the field, we just fix or in group we just fix these terms. So it's just numbers. And then comes this what can be called okay, Tamagawa number is also a number. If G is simply connected, then Tamagawa number is 1, or at least conjectured to be 1. And then there is this huge Euler product. However, Euler product can be expressed as product of zeta and L values. So after some time, I realized that most of the actually all of the factors in the volume formula are possible to estimate. Say you can prove that this Euler product is bigger than 1 and smaller than 2 without too much, well, in certain cases, with very little work, although the definition is complicated. And then discriminants also you can control. So this, already after estimation, I could see that my first guess about extending, say, Hurwitz 237 triangle group to dimensions 4 and higher was not going to work. There is other manifold which has minimal smaller volume, orbifold which has smaller volume. Well, and eventually so I obtained results for even dimensions, and then that results were published in 2004. Also in August 2004, I went to Aberdeen to a conference celebrating Colin McLaughlin's work. And at that conference, I met Vincent Emery, who was very young, just starting his PhD, and he said that he's interested in volumes, as I was, and well, he's interested in studying odd dimensional case, which is much more complicated than even dimensional case that I proved in the paper. So we started working together with Vincent, and then he wrote the thesis about volumes. So he and eventually we published a paper where we were able to treat the odd dimensional case. However, very recently Vincent informed me that he told me that in the paper we missed one case of family of co-compact lattices defined over Q of type 2. So and that may change the results in large dimensions. We are going to, well, this needs to be checked, but by now just I have to put this restriction that the first theorem applies only, the proof of the first theorem covers only all the details of the first type of arithmetic lattices, and yeah, they might be an addendum to that paper with Vincent. Somehow, once again, we work a lot on volumes. The results sometimes give new surprises. Well, so there are these functions here, which I denoted omega c and omega nc. These are very concrete functions. Here are the formulas. Here are the formulas for omega c, very long formulas coming from my paper and our paper. But well, when you look at these long formulas, you see that this is a very concrete expression. You can calculate it, you can estimate it. So, well, you fix dimensions, say n equals 2r, r even. Then this is just a number, and this is another number, depending on the dimension, so the product. And then there is zeta value, which dedicated zeta value of the field Q root 5, which again can be computed explicitly in this case. So, well, and these factors, zeta and L functions, which appear in the volume formulas, volume computations, they indicate a deep arithmetic connection of volumes with number theory, prime numbers, and all the rest. And later on, we will encounter also connections with class numbers. So basically, all number theory get merged into some form into volume formulas, reappears there. This is another very long slide with formulas for volumes of non-compact quotients. I will just flash it, again, emphasizing that the formulas are concrete and computable, easy to calculate as soon as you have them. Few words about proofs. So how do we prove these theorems? The first and the main ingredient in the proof is Prasad's volume formula. Then, well, it gives you control over the volume, but you need a final control over together with Brouillet's theory that allows you to handle the situation over non-Archimedean completions over the number field. And then using bounds for discriminants and class numbers, you can do estimates, and together with Prasad's formula, Brouillet's theory, you use these estimates to single out the examples that tend to give extremal values. And then in order to check that these examples are indeed the extremal examples, there are some techniques using Galois cohomology, algebraic groups that allow you to do final analysis. And in particular, often it's very difficult question to say that this lattice itself is a maximal lattice, or perhaps it has a order 2 extension, which is maximal. So to rule out this small index, usually power of 2 extensions, okay, subgroups, is a very delicate problem where we use results of Rolls and Gopal Prasad, Galois cohomology. Well, I gave a talk about volumes at the ICM geometry section in Seoul, and this is the graph from this talk, which I can show here. So it shows, I said that the values are computable, but in the graphs you actually see the depending on the dimension. So here is dimension 10, here is dimension 20. It's almost, well, you can continue. So the first graph is the volumes of the smallest non-compact orbifolds, and the second is for compact ones. Surprisingly, when you look at these graphs, you see a few things. So first surprising thing that the volumes of non-compact tend to be smaller than compact, which is quite counterintuitive and does not happen in small dimensions. The second observation is that, okay, the volumes of compact, they decrease up to something like dimension 8 and then start to grow very quickly. Actually, you cannot see it from this graph, but it happens also with non-compact ones. So they decrease up to dimension something like 18, and then they start to grow, and eventually also minimal volume grows super exponentially with the dimension. These are some corollaries which are interesting from geometric point of view. Finally, let's come back to my initial question. That was my motivation for the paper, for studying volumes. So using results obtained from Prasad's volume formula, I could show that the minimum of 4-dimensional hyperbolic arithmetic manifold, if it has Euler characteristic smaller than 22, so Davis manifold has Euler characteristic smaller than, well, equal to 26. And then, okay, if chi is smaller than 22, then it has to be a subgroup of index depending on chi of a Coxeter group. It's not the same Coxeter group which Davis used in his construction, but it's like a twin Coxeter simplex group. So it's a very concrete statement, which in a sense reduces the problem of finding minimum volume to a computation, but computation is extremely hard. So later Condor and Marson Condor and Colin McLachlan, and independently Cormac Long in his thesis, they didn't run the whole computation. It's not feasible. However, they did some clever computation and managed to find Euler characteristic 16, several examples of non-isometric hyperbolic form manifolds with chi equals 16, all covered by these, all covering this or before. And okay, it's not known if there are any examples with orientable manifolds with small compact hyperbolic form manifolds with smaller Euler characteristic. And in a related work, also using Gopal Prasad's volume formula, Vincent Emery showed that for dimension higher than 4, so Euler characteristic 2 would be not possible in this kind of problem. So, well, we are still in search for the simplest hyperbolic for compact hyperbolic for manifold, and the same in higher dimensions. However, now we know much more about this, and for orbifolds we have a complete picture, arithmetic orbifolds. I would like to mention some other related results on minimal volume. So around the same time, Alireza Salehi-Goussefidi worked on analogous problem in positive characteristic, also using Prasad's formula, and he was able to solve this problem in positive characteristic. And okay, let me jump more. Very recently, Alireza's student, Francois Tiumani, solved minimal problem for lattices in SLNR. This paper is published last year. And somewhere in between, I have this citation to paper of Vincent Emery and Matthew Stover, who found minimal covolume non-uniform lattices in say complex hyperbolic spaces of arbitrary dimension. Well, as you can see from this list, it's not complete, but it's quite representative. There are still quite many open cases. For instance, covolumes of uniform lattices in PUN1, we don't know the minimal volumes. And okay, there are some other groups, not to mention exceptional groups. Perhaps in this set, I should also explain, discuss the work on Gopal Prasad and Saiki Jung on fake projective plane spaces. Also, it is also directly related to minimal volume problem and applications of Prasad's formula. However, it's a big work, and fortunately we have another talk dedicated to it, so I don't mention it. the slides. Well, so there are many gaps in this picture. However, there are other problems which I am going to discuss in the second part of the talk. Also, the problem about lattices and covolumes of lattices in semi-simple Lie groups, and it is also the problem which was studied and to large extent solved using Prasad's volume formula. So now we are going to talk about growth of lattices, and first about subgroup growth of lattices in semi-simple Lie groups. Well, so after postdoc in Bonn, I came to Jerusalem, and I was in the Institute of Mathematics at a seminar. It was in fall 2003 when Aleksy Lubotsky gave a talk about their recent work with Nikolov and also Goldwyn and Piber, in which they count congruent subgroups of lattices in semi-simple Lie groups. So I'm going to say what they count, and to briefly state what they obtain. In order to do so, I need some definitions. Well, let LH, you know, the number of conjugacy classes. It's natural that we consider lattices up to conjugacy. Equivalence of lattices whose covolume is smaller than X. You fix a Lie group, H, semi-simple Lie group for this talk, and you fix a Haar measure, mu on H. And then you compute reduced measures, and so you're interested in the number of different lattices of covolume less than X. And the same for arithmetic lattices. So why you are interested in these numbers? Firstly, Wong, using the previous work of Kazhdan and Margulis, proved that there is always a minimal volume. And Wong showed that actually you can prove that even stronger, the set of volumes is discrete. And so this number LH of X is finite for every X, except that when group is PSL2R or PSL2C, where there are accumulation points in the volume spectrum. Well, for PSL2R and PSL2C in turn, as well as for other semi-simple Lie groups, Borel proved that the function which counts arithmetic lattices doesn't have volume accumulation points, and so it's finite for every positive X. And here comes a natural question: what is the behavior of these functions? In particular, what is the asymptotic behavior of these functions? These functions are not exactly what Aleksy Lubotsky and his collaborators studied in their papers. However, they introduced them already there. Well, there is some motivation to study these functions, first coming from physics. There are a couple of papers by Steve Carlip, and there is a story that Steve Carlip met Thurston and asked him questions about this counting lattices in certain particular Lie group. And Thurston asked Lubotsky, and then Lubotsky started working on it. So there was another paper by Lubotsky, Gilander, and Moses, which kind of kicked off the subject, and I'm going to mention it later. And also another motivation which we discover during the work on counting lattices is that these questions appear to be deeply related with very deep and interesting problems in number theory about distribution of primes, discriminants, and class numbers of algebraic numbers. So, well, what Lubotsky and collaborators proved in their papers published in 2005 was in particular the following result, that whenever you take a simple Lie group of real rank at least 2, so for instance SLN R for n greater or equal than 3, you assume generalized Riemann hypothesis and third conjecture about congruence kernel. However, for many particular groups and particular arithmetic subgroups gamma in H, you don't need to make any assumption. These assumptions are necessary in the whole generality, and I'm not going to go into details, but I want to mention that in many cases you don't need to assume any open conjectures. Well, third conjecture is known to be true for many groups, as we know from Andrei Rapinchuk's talk and their work with Gopal and the work of many other people. All right, so they prove that there is a limit of subgroup growth function Sn of gamma, subgroups of index n, counting subgroups of index n in gamma, and the limit surprisingly does not depend on gamma. It depends, so the asymptotic of this function depends only on the Lie group, and there is a constant which there is an explicit formula in terms of root data of H given this constant gamma at H, and the limit is always for every lattice will be equal to gamma of H. Very well. So in the same papers and then also in the book with Siegel, Lubotsky asked a question or conjectured that there should be also a limit of the function which not just counts subgroups of a given lattice, but counts all lattices of bounded volume, and that the limit should be the same as so the whole counting should be dominated by any one single lattice. So this is what Alex presented in his talk, and of course with the proofs and more illuminating details. And after talk, I came to Alex and said that, okay, but I think I know how to prove the conjecture because I know volume formula. And okay, he said, well, very good, write the proof and we talk next week. So that is how I started to work on another problem, another application of Prasad's volume formula, which is in counting lattices. So, well, what was the idea of the proof, which I had? So first we need to count finite index subgroups in a given lattice, which was already done by Goldwith, Lubotsky, Nikolov, Piber. Now, the second main ingredient is to count maximal lattices. And this is where I said that I know how to do it because I know Prasad's volume formula. The idea is that Prasad's formula allows you to control very well volume of principal arithmetic subgroups and also of maximal arithmetic subgroups. And okay, it's when you are familiar with this formula, you realize that actually the number of maximal lattices will have to grow slowly. It was also the conjecture of Lubotsky, and this is why he made a conjecture about growth of lattices. And then, okay, you count maximal lattices. Supposedly you get very slowly growing number, and in each, then you combine 1 and 2 in each maximal lattice, you count subgroups of bounded index, and so you kind of multiply and have the general asymptotic. So this was the plan. Well, apparently, I'm going to talk about this, but surprisingly, this part 3, that looks trivial on the first side, appeared to be a complicated part. Part 2 is also not as easy as it seems. Well, so 2003, I started to work on this, and the first part was to count maximal arithmetic subgroups. And here I was able to prove the following theorem, which was later published. So it says that the number of maximal arithmetic subgroups of covolume bounded by X grows at least polynomially with X, and in fact very close to polynomial, where beta of X is certain function. You can make epsilon arbitrarily small, but then the constant grows. So it's not quite polynomial bound, but you can make it as close to polynomial as you want. This part about beta of X and log X to the power epsilon comes from the work of Jordan Ellenberg and Akshay Venkatesh. So what they did in their first joint paper publishing annals some time ago is they counted number fields of fixed degree and bounded discriminant. And what I wanted to do is to count number fields of bounded discriminant without any fixed degree. And if you know how the discriminants of number fields behave, again, you expect that the same count as Ellenberg and Venkatesh had in their paper would apply. And I have some naive argument how to prove that, but I asked the authors, and they come up with a very nice proof which shows that, yeah, the same asymptotic would apply. So that gives me this very good upper bound. Also, in non-co-compact case, we do have polynomial growth. All these constants a, b, a prime, b prime, they are computable. However, it's the numbers. So the numbers for a's we get are very small. The numbers for b's we can get are very big. And if you want better numbers, you encounter difficult problems. So this is what about counting maximal arithmetic subgroups. In fact, I wrote a first draft of paper where I put this maximal counting, and then second theorem was proof of the conjecture of Lubotsky. However, and then I showed it to Tsahi Gilander. I sent him a preprint, and he quickly noted that the proof of the second theorem had a gap. It's an interesting gap because it comes from the fact that, like, when you multiply two numbers, you have to be very careful with error terms, and I was not careful enough, so error term could potentially accumulate. And that was okay. At that time, I decided to cut the second part of the paper and continue thinking about it. And we continued thinking about it together with Alex Lubotsky. So some 5 years later, we published another paper jointly, where we could show that the function h of x grows at least as x to the power a log x, and at most, if we assume convex subgroup property, Serre's conjecture, and Margulis-Platonov conjecture. Okay, you can see more about Margulis-Platonov conjecture about normal subgroups of certain conjecture about centrality and normal subgroups. It is explained well in Prasad Rapinchuk's paper on congruent subgroup problem in Milner's volume. So if you assume some well-known and proved in various cases and widely believed to be true conjectures, then you have also upper bound. Note that, okay, note that I'll show this already. Part one of the theorem disproves Lyubodsky's conjecture, because Lyubodsky's conjecture said that the growth there should be a factor here in denominator log x, so the growth should be much, for large x should be much smaller, but we prove that it's faster. So from where comes this fast growth? The fast growth comes from interesting number theory. If you so I mentioned the error term which accumulates, and somehow it accumulates very quickly if you go along an infinite sequence of unramified extensions of a number field. So if you go along a class field tower and do all the computations with Prasad's formula, actually in this argument you need to be able to define algebraic group over admissible algebraic groups over all these fields, which would contain arithmetic lattices with controllable covolume. And to this end, we ask a question to, I always ask questions to Gopal, so I ask question to Gopal and to Andrei Rapinchuk, and well, they wrote a paper answering our question, so we use a very nice other paper by Prasad Rapinchuk to prove this first part of the theorem 4. And well, here is an open problem. We don't know anything. Well, we can prove that there is number A and number B, but like if asymptotically one can prove, one can put some constant here and then some error term. We don't know anything about the limit log LH divided by log square x. Well, let's continue. And here's another result proved using Prasad's volume formula. Actually, this result is proved using Borel's volume formula that Armand Borel obtained earlier. It's a formula for covolume of arithmetic subgroup of PSL2R and well PSL2C. So in the case of PSL2R, the total number of lattices is infinite for large x. The number of arithmetic lattices is fine, and we are able to compute the limit of the asymptotic growth of this number. Okay. Yeah, it's equal to 1 over 2 pi. This computation requires a delicate analysis of representation theory of Fuchsian groups, which we were able to do thanks to our colleague Arne Tralle. And well, it requires volume formula to control the growth of maximal lattices, in this case Borel's formula, and it requires a good control over the number of generators of a lattice in terms of covolume, which was proved by Gilander. And so one of the applications of this argument of Gilander, which can be extended to any any semi-simple Lie group shows that, well, gives an alternative proof of Kazhdan-Margulis theorem, which only uses Margulis lemma and Morse theorem, some topology. So we have this result, and for dimension 3 we also have result, but now we don't know again any. We have estimates, but like extremely rough for alpha and beta, and we don't know if there is some nice number that comes out here. There are some corollaries of these results. Let me mention that, okay, this was obtained later after my paper. So in my paper about counting maximal arithmetic subgroups, I didn't treat PSL2 case, but this can be extended. Also, Gopal Prasad somehow in their fundamental work on discreteness theorems of for lattices in semi-simple Lie groups, it's published in the same volume, and it's perhaps the first and definitely one of the most important applications of Prasad's formula. So they excluded PSL2 case, but it can be added there. And also something that I'm not going to talk today because I don't have enough time, but the results obtained using Prasad's formula, in particular on counting maximal arithmetic subgroups, could be used to study arithmetic reflection groups. And this, well, together with other results. And this is subject in particular of our joint work with Agel, Storm, and White. So, well, finally, considering growth of lattices, I would like to talk about one more theorem, which is like the second part of theorem 4. So let me go back. You see, in theorem 4, we consider all lattices, but in fact the growth here comes from co-compact lattices. The observation we had with Aleksy is that if you restrict to non-co-compact lattices, you can do better. So non-uniform lattices, and it's not because the counting of maximal arithmetic lattices is more precise in this case. It's because you cannot do class-field-Taylor constructions. So the field, the degree of the field of definition is fixed, and then error term in counting maximal lattices does not accumulate anymore. So, well, with a lot of effort, we were able to prove that the Lubotsky conjecture is actually true if you restrict to non-uniform lattices. So the limit exists and indeed equals this explicit constant gamma of h, at least for what we call two generic simple Lie groups. So what is two generic? Two generic means that we exclude certain types of groups, but we cover almost all classical groups and some exceptional groups. And well, so why do we need to assume these two generic? This is an interesting part. So, okay, conjecturally, we don't need to assume this. And this conjecture is equivalent to a conjecture about class numbers, or about asymptotic growth of the class numbers of algebraic number fields of a fixed degree. So, well, the first instance of this kind of result about the rank of class group is the celebrated Gauss theorem. about 2 rank of the class groups of the quadratic number field, and there indeed we assume this kind of even better than this asymptotic. However, conjecture like this appeared before in number theoretical papers. In particular, it appeared in some very similar question appeared in a paper by Brumer and Silverman. So it's widely believed that the rank of class group grows slowly with the when you vary the field along the fields of given degree, but it's a very hard conjecture, widely held. So well, our theorem in a sense gives another motivation for this conjecture to be true, because if you have a nice result like this, you don't expect some, say, groups of type A to be excluded from the general picture. And so, in fact, if you were able to prove this theorem 7 for any other group, so any group which is not too generic, then you immediately get some result about class numbers following this equivalence which we developed in the paper. So, well, for me it was quite striking result to see class number. You see also discriminants, and you see primes like GRH appeared in quite a few formulations. Well, I'm going to finish on mentioning some other papers, again, a non-complete list, but some other references for applications of Prasad's formula to count lattices in semi-simple regroups. In fact, the first 2 papers don't use Prasad's formula. In the first paper, I mentioned it briefly before by Berger, Gilander, Lubotsky, and Moses. It was written in a response to question of Carlip and Thurston, and they were able to to prove counting results of the type which we discussed for hyperbolic manifolds. However, here arithmeticity doesn't play key role. In fact, their construction is non-arithmetic, and the key ingredient is the fact that you start with a large group, and then so that has finite Dirichlet subgroups which surjects into a non-abelian free group, and then from that free group you get a lot of finite index covariance, and so this is the very rough idea of counting hyperbolic manifolds. Then there was an important paper of Sahi Gilander, homotopy type and volume of locally symmetric manifolds, where he considered this type of counting questions without using Prasad's formula, more topological methods and the theory methods, and he obtained important results. And this paper was one of the motivations for me to study counting lattices. Well, at about the same time as we worked in characteristic 0 case on the number fields, Alireza Salihigol-Seyfidi and also Alireza together with Amir Mohammadi, I don't mention their joint paper here, but they worked in counting in positive characteristic and in p-adic groups, and this one of the papers which was written, so counting lattices in simple Lie groups, the positive characteristic case. And there the growth is different. The results are quite different from characteristic 0. And the Prasad's formula plays, again, a key role in these calculations. Finally, I mentioned another paper of mine joined with Ben Linovitz, where we count isospectral manifolds. So this is, in a sense, a continuation of our work with Lubotsky, published in Advances as well, where so we were able to use some results from that paper and to add a few more ingredients to be able to count isospectral manifolds. And we obtained quite surprising result that the number of isospectral manifolds in higher rank grows very fast, almost as fast as the total number of manifolds. And well, there are some conjectures also that appear in that paper. I think there are interesting open questions there, which one can find. So, well, this is the end of my talk. Thank you very much, Gopal, and thank you very much, everybody who listened.